isn't Google wonderful? How can we live without it? I thought this was amazing when I was watching this last night.
2, 1, see ya.
Guess it's closed caption, so you can see. Well, you don't. I don't think you need much captioning to go with this. This guy who lives in the southwest of England, a place called county called Somerset, by the sounds of it, and he wants to get the world record for the flying off jumpsuit. What they call it? Flight suit? No, not flight suit. What is it? Flying wing? Wingsuit. Yes, of course. Yeah. All the permutations, but not wingsuit. He wants to go off the highest, be the highest one to do it, I guess, highest elevation. I don't know if it's highest total elevation from where you take off to where you land, or highest elevation starting. But anyway, seems crazy to me. You'd never catch me doing that. But yeah, looks quite liberating. It's quite amazing to see people do it. And then I guess you have to get it right, because you have no engines to get you up if you're a bit low when you're swooping over something, I suppose. So yeah, very, very interesting. And I guess it's interesting that they have I guess it makes sense that you have a parachute to land with. I don't know if you could just kind of stall out with your wings and just by pointing yourself up. But actually it's no different from the things we're talking about. There's definitely some fluid mechanics in here, right? You're basically a wing, your own wing, with the principle only is that fluid flows on a longer surface on the top than the bottom, and so since it has to join up from continuity at the leading edge and the trailing edge of the wing, it has to go faster over the top. We know if things speed up, as a consequence of speeding up, you have to drop something. If you can't drop elevation, you have to drop pressure, and as a result of that, you have lift, which you could calculate from the force pulling up just by the change in pressure divided by the area. So yeah, so interesting stuff. What else is closer to what we're talking about? I don't know how to stop. Why can't I stop this? So I guess that's stopping it. You saw that last time. We saw this last time. Did we see all of these last time? I don't want to talk about that. Yeah, we saw all of those last time. So perhaps that's all we need to look at this morning for eye candy. Well, we did talk about at the end of our set last time, we were talking about porous media flows. And so the grids on which you would do those would look something like this. We did talk about the fact that we could solve the problems of porous media flow. It's an energy equation. The essence of the behavior is that you lose pressure as you go from upstream to downstream. With Bernoulli, you can't do that, because if you have a pipe which stays the same cross-sectional area, as you go from upstream to downstream, the velocity can't change. If it's horizontal, the elevation doesn't change, and therefore the pressure can't change if there are no losses in the system. But the way that we solve porous media flows for petroleum engineering or environmental contaminant transport, flow that underlies contaminant transport, is to use only the continuity equation, which says mass in equals mass out, and the difference between those is accumulation. That's what our conservation of mass term says. Then we can solve them through a little shenanigans that we tried last time. And so maybe we can look at that. So that's where we'll follow on from today. So what we'll do today, if I bring the things up that we had, did I open it already? I think I got to where we were. Well, this is what we'll do today. Get it across the whole thing, open this. We won't do that. We didn't talk about that last time. Yeah, okay. These are the things we'll chat about. Recap first, but then maybe we'll just finish off what we talked about in terms of flow and porous media. We'll see that we can solve lots of porous medium flows and external flows, flows around wings, by using something called stream potentials. And then we will look at conservation of momentum equations, where our forces are equal to velocity times this equation here, to solve for open flow problems. So we didn't really look at this morning, but we make the distinction between what we talked about here in terms of flow within porous media and what we might look at in flows which are actually external. So instead of flowing within porous media, these are free flows. It's water sloshing around in a bucket with no porous medium in the interim. And to do that, we can't use Darcy's law or flow within porous medium to apply the frictional losses. So you have to do it in a different way. And so we'll look very briefly at that, just because it's an important thing in solving flows like this. Not that we'll talk about solving flows like this. So that's our plan. So let's go back to maybe what we had last time. This was just to remind you, we talked about this being, as I called it, pretend conservation of momentum, because we're really only solving conservation of mass. We went in and we looked at this differential cube. We looked at the velocity going in, velocity going out, the fact that it has to change velocity as it goes across it. And if we sum those masses in minus masses out, we get that the sum of the masses is just equal to density, volume of our little cubic element, times the change in velocity with y as you go across this length. If we resolve in each of the other directions, we end up with 3 derivatives in the component. If the sum of mass is equal to a steady state problem, then it equals 0 by definition. And so what we can do is we can write the velocity term in terms of Darcy's law, either in terms of a pressure gradient or a head gradient with different terms before it. We throw this into here, and if we do that, we end up with something like this. Of course, the other thing that we could do is we know that this, for a non-steady problem, is just equal to volume times the change in density, still equals 0. And so these are steady state problems. So, and if you look at the flow within the system at a snapshot now and 10 minutes later, the flow velocities in the system don't change. But for non-steady problems, we can accommodate it by looking at this. And I guess I was going to talk about it last time. It's actually pretty straightforward. That what we can do is we can write this term out here. That's just the volume of the element multiplied through by rate of change of density with time, which this is. I guess we could write this in terms of pressure over pressure, right? And if we sort this out into a volume multiplied by d rho dp, my p's and rho's start looking the same. This is a rho, this is a p. This is a dp dt. So in other words, I'm pairing these two together and pairing these two together. That's all I'm doing. And then we can define this. We had the definition of compressibility was equal to 1 over rho d rho dp. Oops. 1 over rho 0 dp d rho. And so we have this term here, and we have this term here. And so I guess we could write this out as being change in pressure. It's the opposite, right? So I guess it's d rho, this is d rho dp. Wrong, bad derivation. By definition, this is, write that out. think I got it backwards. The units of this are 1 over pressure, so it has to be d rho on the top and dp on the bottom. The densities cancel out, so it's 1 over pressure. And so if we substitute this, we just rearrange this, get rid of this, rewrite it in terms of d rho d pressure, perhaps I put a little cap on the bottom, is equal to compressibility multiplied by initial density, and a minus sign to take the care of the right sense. And if we put this into here, then we have this extra term being volume multiplied by compressibility multiplied by initial density, negative sign, which is this term, and change in pressure with time. And so this whole term here is representing this. And so what we could do is just add it to this individual term. So the flow equations end up being something like minus volume, I'm just going to write this term out, the compressibility of the fluid, the original density, multiplied by change in pressure with time, is equal to this term on the right-hand side. Just take one of these, and it would be density, volume, and change in velocity with location. And we can substitute this term in here. So the petroleum flow equations, we can get rid of density and volume on one side. And we have, that's a plus and equals 0. And so we end up with an equation that looks like compressibility, change in pressure with time equals change in x and this term here. Times these constants that go outside it. So you'll see this in your other classes. I guess in your undergraduate education, you wonder for the first 2 years if you'll ever see anything of relevance to you when you're taking your chemistry and math classes. Maybe in the beginning of your junior year, I guess that's where we are, you start talking about the foundations of some of the things that you'll use. So this is the flow equation that defines how a pressure gradient drives flow within a porous medium. It applies the shear resistance to that porous medium, that is the loss as you flow from upstream to downstream, which is the essence of porous media flows. You can imagine that if you're flowing through very small pores within a porous medium, there's lots of drag on the fluid that goes through there, so there's a big pressure drop between them. So the essence of this is to be able to do that. And if you deal with this so this is the way it's written in terms of flow, where you define it in terms of pressure. If you define the behavior, as we alluded to last time, that you could also represent this as a head, Z1 plus P over gamma W. I guess you could think about this as being P over gamma W would be the height of this. Then you can also write this as a surrogate equation, which looks like this. So if you're looking at groundwater flow, the equation is kind of often written in terms of a term. It's called specific storage, a change in hydraulic head with time being equal to a hydraulic conductivity multiplied by d2h dx squared. And so all we've done is we've replaced the pressure with another term, which is hydraulic head, which is equal to the elevation head plus the pressure head. So it kind of intrinsically includes this. These are different coefficients which are governing the behavior. Perhaps in this class we don't need to worry about what they are. And so this is the preamble for what we'll talk about today in terms of stream potentials. So we will take this groundwater flow equation. Now that we've derived it in terms of the transient behavior, we'll assume that it's steady state. And if it's steady state, we can write it just in terms of this second order PDE. And we'll use that to be able to say something about flow in porous media. So that's kind of finishing off what we said last time. So I'll rewrite those expressions as we move down here. It's the only important thing that we need to have them. So this is kind of what we did. So we took mass in equals mass out. We assumed that the volume of our control volume isn't changing with time. We assumed that the compressibility of the fluid in a standard box is changing with time. And this is what we used. We used this we basically just now derived this expression. This is what we did on Wednesday. This is what we did this morning. And the outcomes from this, again, I'll reiterate, we're just using conservation of mass, not conservation of energy or momentum in this, conservation of mass only. We ended up with two expressions. One was specific storage, rate of change of head with time. You'll see this for the environmental systems engineers who are doing GSci 452 this semester. Hydraulic conductivity, d2h dx squared plus d2h dy squared. So that's an important expression for us today. And to keep the petroleum engineers happy, actually has a porosity term in here as well, which we didn't mention, because the pore space is mainly solid. So in the porosity, it's only in the porosity that you get the compressibility of the fluid. Let's not worry about that. And this is permeability over fluid viscosity multiplied by d2p dx squared plus d2p dy squared. So if you want me to define those terms, beta is equal to compressibility of the fluid. So you remember it's 1 over pascals. K equals permeability. Which is in units of meters squared, surprisingly enough, although maybe we'll see why that's the case today. Specific storage is SS. So I can't, they're in units of 1 over length, I think. They're strange units, so I'm not going to define them. And these are the accumulation terms. So these would allow fluid to accumulate in a given volume, just like filling up a tire with gas. The volume of the tire doesn't change, but the density of the fluid changes slightly to accommodate the fact that you're pushing it in. Mu equals viscosity, dynamic viscosity, which is in units of Pascal seconds. And water is 10 to the minus 3 Pascal seconds, right? And the other commonality is that P equals pressure. H equals hydraulic head, which equals elevation head plus pressure head plus velocity head ignored. And I guess the other thing is that we could relate these two is that what was a good expression to know? Permeability divided by dynamic viscosity is also equal to hydraulic conductivity, which I didn't define, density of water, gravity. So I guess I didn't define hydraulic conductivity, which is in units of meters per second, length over time, velocity. So that's kind of background. I feel obliged to kind of define those terms since we use them, but you don't really need to know that today. What we're going to explore is the fact that if we go back to the wingsuit guy, he was a guy, I guess, then we can think of him as a airfoil. And we've always messed around with this, with the, I don't know why I did such a small airfoil, is that we can think of a stream tube on top of this and a stream tube below this. Wouldn't be an unreasonable thing to think of. And I guess that you know already that the idea is that the air impacting here has to join up on the trailing edge of the airfoil with the air that was here before. And so if it's traveling a longer distance on the top, it has to go faster. If it goes faster, then Bernoulli tells us that this plus elevation head plus pressure head plus velocity head equals constant. That's why we can draw that diagram with the upstream and the downstream portions of our tube. Then if by definition, by going from here to here, and the same molecule of air, of nitrogen that was split here, half of it going over the top and half of it going over the bottom, if it's traveling further on the top, then it has to go faster. It's going faster, then this goes up. If this is going up, then elevation isn't changing very much, so the pressure has to come down on the top half. If the pressure on here is reduced, then by definition there's a net force going up because there's less pressure on the top than there is on the bottom. That's just the deal. So you'd know that's how an airfoil works. So it'd be interesting that we could do something about the flow patterns around this. So we're not going to do that today. It turns out that the equations that we're looking at, which would be something like d2 phi dx squared plus d2 phi dy squared equals 0. So in other words, if we make these time-dependent terms go away, even though they might be quite important in some of the things we're trying to do, then both of these equations are equal to 0. We don't care about the constants ahead of them. And so we can do something with this. So this is generically some term. It turns out that if we look at this, and I won't go through the math, it's kind of irrelevant, it's called stream potentials. Yeah, actually it's quite short math, but I still won't go through it. It allows us to be able to say that we can define a bunch of stream tubes or streamlines, which are these, and the streamlines would be the trajectory that an individual particle of water, packet of water takes, molecule if you want to think of it that way. But the interesting thing about this is that orthogonal to these streamlines, we can draw a bunch of what we'll call equipotentials. And the rule is, for us, if we make this, is that these equipotentials and the streamlines, so I guess these are equipotentials, equal potential. And that's what this term is here. So we can think of the potential as being the head, which is equal to the elevation plus the pressure over the unit weight, the fluid. If we want to, v squared over 2g term ignored. So equipotentials mean that everywhere along this line, the value of the head is the same. It's the same on this line as well, but a different value. And the rule is that equipotentials and streamlines, they have to intersect at 90 degrees to each other. Won't go through the math for it, just a little bit of differential tomfoolery, if you like, to be able to do that. Doesn't matter. It means that we can draw nets. And so the idea then is that we could think of drawing a flow net, so that's what we'll talk about. Which is a really quite a powerful technique. And I'm going to keep with those colors. And so if you think about flowing between two streamlines, so I'm being true to our previous color scheme and drawing across this Is that a yawn? Were you up later than me last night? So, streamline equipotentials, I won't label them. Let's label this length dl, or it could be just L. Let's label this width dw. What am I going to do now? Yeah. So we'd like to know something about the volumetric flow rate through here, or the velocity. And so how do we get that? Q is equal to cross-sectional area times velocity. Velocity we could write as being equal to hydraulic conductivity times dH dx, dl in this case, right? We're flowing from upstream to downstream. We could think of this as being H1 and this as being H2, two different potentials. We know that the flow between these streamlines has to be confined within these streamlines because this is essentially a stream tube. And so we could write that. We know, I guess, also that the area is equal to dw times the length into the page. And so we could write this out, I suppose, but just by doing that substitution, getting very creative in my colors, as equal to dw times k times dh over dl. The second part of our streamline is that we said that the streamlines and the equipotentials are orthogonal to each other. The other thing that we can choose to do is that we can make these nets equidimensional, so that the width of them is the same as the length, so that they're kind of distorted squares. And if dw and dl are the same, then these two terms together go out to be equal to 1, right? So we get rid of that. So this is equal to k times dh. And now if I redraw this stream tube as being two streamlines that go from upstream to downstream, and I draw these equipotentials. So H1, H2, H3, I'm trying to draw them so they're squares. I'm not sure if I'm succeeding. So the only thing we have to mind is that we're drawing them as squares. So this would be H2, H3, H4, H5, sorry. We could think of this as being a total change in head as you go from upstream to downstream, which we'll call delta H. And so we could also write that, oh, that's good, quite a good one. Didn't know I'd get that. We could also write that H1 minus H2 is equal to, running out of space, delta H over N sub D. N sub D is the number of drops. For want of a better word. And number of stream tubes. Should be one word, is, for want of a better term, NS. So, taking this term here, volumetric flow rate is equal to K hydraulic conductivity times the change in head, which is equal to K times H1 minus H2, which is equal to K times the total head drop across the system divided by the number of drops. So this is the flow in one stream tube. If we look at the flow in all stream tubes, again, bad handwriting, then Q all equals QS times the number of stream tubes, which equals NS over ND K delta H. Incredibly simple formula, but actually very effective. That's it. So we got to where we want to be. And so there's an example, I guess, as we look through it, that we can look at. So I could draw a flow net here. So this, what we've said is that we know that these cross perpendicular to each other. We know that if we draw them as kind of distorted squares or cells that are square, then a couple of the terms cancel out, and then this equation becomes the equation that defines flow within the system. So if we wanted to, I could imagine that, you know, one engineering problem of significance would be, I don't know, you want to build a building downtown to put your brew pub in. You put a sheet pile wall in that is this, and then you excavate on the other side of it. Sheet pile wall to stop the stuff falling in. You must have seen these in town. Also, if the water table is at the surface, then it's also to stop the water coming in. If you get a puddle in the bottom that develops here, then the water table would be here. You'd pump it out, and you'd put the sheet pile wall down deep enough so you didn't get the water, a ton of water coming in. So how do we solve that problem? What do we have? Blue for streamlines. So I don't know how good a job I'll do with this. I'm not very good, but good enough. You see where we're doing. Lousy job. You could probably do better. So I'm just satisfying the fact that streamlines and equipotentials cross at 90 degrees. They give you boxes which are roughly square. Be a little bit of a strange one here. We're getting kind of triangular in this little zone here, but don't worry too much about it. Doesn't matter if you get exactly the right geometry as me, because we'll just number these things. What else do we need to know? Well, here, P equals 0, Z equals Z1, V equals 0 for all intents. We don't care about V. Here, P 2 equals 0, z equals z2, and again v term doesn't matter. So actually delta H in this will just be from, it'll be just equal to equals H1 minus H2, which equals Z1 plus P1 over gamma minus Z2 plus P2 over gamma. This is 0. This is 0. So it's just this length. So this is just delta H, physical length. Number of stream tubes, well, if we write NS on the top, would be 1, 2, 3. Yeah, bless you, I'm supposed to say that. And number of drops, zero. So that's not a drop, right? That's a drop going to one drop, two drops, 3 drops, 4 drops, 5 drops, 6 drops, 7 drops. Should have been green, of course. 8 drops, 9 drops. Flow rate is equal to 3 divided by 9 times hydraulic conductivity, I don't know, 1 meter a second, times delta H. Didn't put a number on it. 10 meters. That'd be 30 feet, 3-story building, right? Depth of a parking lot, parking garage. And that's it. So from the units of this, obviously these are unitless numbers. This is length over time. So the units, if we wrote it out, would be equal to meters per second times meters, which is equal to meters squared per second, which is equal to meters cubed per second 1 over meters. Right? So volumetric flow rate is meters cubed per second, volume per unit time, but it's per unit length into the page, per unit meter into the page. It's an incredibly simple way of doing things. So it turns out that you can also do it, use the same technique for flow around airfoils. It doesn't have to be flow in porous media. It works quite well, even though we know that the velocity squared term might not be small here, but maybe the velocity squared term isn't changing very much. If this stream tube isn't really constricting, then the velocity as you go from upstream to downstream from continuity, right? We know it's equal to V1A1 upstream, V2A2 downstream is our continuity equation. So if the width of this stream tube isn't changing, then the velocity isn't changing very much along here. And so the only thing that makes this term important is inertia. You're accelerating a fluid as you squeeze it through a smaller part of the stream tube, and you can't assume that this term goes away. So it works well for airfoils as well. And so there's another example in here, I guess. I don't know. We could do it again. Maybe it's a bit more complicated than the previous one, but you see it has exactly the same attributes. Width and length are the same. Flow quantity is defined the same. We can calculate the flow rate through the system is equal to number of stream tubes over number of drops times hydraulic conductivity times delta H. And here we can also prescribe. It seems a bit stranger that this is an equipotential. This is an equipotential here. Why is it an equipotential? Well, if you think about this being open and a swimming pool on the inside, then the pressure change in here would be equal to this. So this would be P over gamma. And the other part, going vertically upwards, would be equal to Z. Or here is Z. So all we're doing is we're taking a datum at any point. Actually, it would make more sense if we took the datum at this point here. It doesn't really matter. And so as you go up to this point here, you know that the pressure is equal to 0, but the elevation is equal to this amount here. And as you go progressively deeper down, you just swap pressure for a similar decrease in elevation as you go down. So that's all that this means, is that the sum of these two is a pressure plus elevation, and it stays the same all the way up here. Here, the magnitudes would be exactly the same. I guess we could draw it as like this. I guess kind of like this, right? It'd be the opposite. And so this would be the pressure downstream, and this would be the elevation. And so it turns out that all you need to know is what is the head at this point is just equal to h9, which is a length. The head at this point is equal to h0, which is this length here. And so the difference between those is just the physical height of the water table here and the top of this free surface here, right? It's the top of the swimming pool, not the magnitude of this point here, because it's only the top of the swimming pool downstream that it's equal to 0 pressure. And then if you want to use this equation, so this term here would be h9 minus h0, which is really just this, as you can see. This is a bit more complicated because this is a free surface. That's why I didn't do the example first. What do we know about a free surface? Free surface is the top of where the water exists. By definition, the air pressure here is atmospheric, definition of a water table. And so for every single drop on here, this has to be the same change in elevation as you go down step by step by step. Too complicated for us, but just take that on trust. The rest of this equation, well, we know that this is equal to some number. Could be 1 meter a second, could be anything. It's a bit high for permeability, conductivity. And what are the other terms here? Number of stream tubes, 1, 2, 3, 4. Number of drops, 0. 1, 2, well, you know, it's 9, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the last stream tube that's flowing. The head on this point is exactly the same as the head on this point because it has less elevation but some pressure. So this is where it flows out of the porous medium. So this happens to be 9. So, pretty cool. So any geometry that you can draw the right flow geometry for that represents that, then you can get the solution for it. If you're looking at flow into a well, in plan view, you can imagine that flow would be flowing along the slice of a cake, right? So you could do the same thing, equipotential, 2, 3, 4, 5, I don't know, an outer boundary here. So these are kind of squares. You can do the same thing. So flow into this well would just be equal to number of stream tubes, number of drops, K delta H. So if you know the difference in head between this point and this point, if you know the number of drops, 0, 1, 2, 3, 4, 5, maybe 6, you've got this. If you know the number of stream tubes, well, this is the stream tube going into one segment, but you also have one here, and you also have one here. And so this would be stream tube 1, this would be 2, this would be 3. I don't know, you'd probably have 10 of them, right, to be able to do that. So you could get exactly the flow into a well, steady state for that. So I've said too much about that already. Okay. So, well, just to close things off. So we've made the point, and this is kind of a big picture point, that for these flows, remember that we've used only conservation of mass and something that represents the frictional losses, which we've called either the hydraulic conductivity or the permeability to represent this. If we want to represent those flows out of the fire hose that we looked at and the dam break flows, we have to do something a bit more complicated. And for that, we use what's called the Navier-Stokes equations. So if you like, the real energy equation and you could think about that as being velocity times mass flow rate equals the sum of forces. Remember this? This is our conservation of momentum equation plus head losses. So this is conservation of momentum. This is conservation of energy, because it includes the fact that we're not a perfect system. We're losing energy in the system. So this is the energy equation. We could write this as something like a stream tube which doesn't equal constant. I don't know what it means actually, but what it equals. So this is this term here is F. So this is also MA equals F. This is just big picture stuff, trying to explain something in big picture. So Bernoulli with the head losses is the energy equation, one-dimensional flow. It also equals Newton's second law. You're accelerating a fluid that is inertia, has inertia acting against it, and you have to provide a force to do that. That force comprises the pressure head, the elevation, and any losses in the system. So this is just this equation here. So what we could do, although we won't do it, is we could make a little cube and we could look at velocities flowing into that cube. So before we looked at that. So we can look at velocities flowing into the cube, velocities flowing out of the cube, v plus dv, v. And we could account for this equation here, and we'd end up with a very complicated set of equations. Remember that there are 3 of these. And so we'd have a value of a velocity in the y direction, a velocity in the x direction, and a velocity in the z direction. So we'd have 3 terms, 3 equations, 3 velocities. So we'd be able to solve it if we had these 3 equations. But we also have a fluid pressure acting here, which is an unknown. So if we want to solve this open flow system, we have to have another equation to be able to constrain this. And actually, just like Bernoulli, we have to use continuity. V1 A1 equals V2 A2, which is just conservation of mass. So this is one extra equation, which allows us to solve for P. So not examinable stuff, but just big picture stuff. So we could solve for really the energy equation, the real losses in the system, where this little cube isn't filled with porous media, in which case we can use Darcy's law. And if we do that, then we end up with a complicated set of equations, which are these so-called Navier-Stokes equations, which actually have all the terms that we've talked about. So what do we see here? This is a velocity. So in these derivations, they've used velocities in the x direction as u, which we've called vx, in the y direction as v, which we've called vy, and in the z direction that we've called vz, which they call w. And so this is a velocity times a velocity. This is v squared over 2g, all these terms. This is a shear stress. So this is head loss. This is density times gravity. So this is P over gamma. Nope, sorry, that's not right. This is Z. This is the elevation head. And this is P over gamma. A normal pressure divided by a gradient. So these terms embody all the things we talked about. F equals ma would be mass times acceleration. And these are all forces that are either due to gravity, an elevation with potential energy, a pressure that's driving flow from upstream to downstream, or a loss that's scalping energy from our system as we go downstream. And so with these three equations, we have velocities u, v, and w, but we have only three equations. We also have a pressure term in it, so we need some other expression to close it. And so the expression to close it will be continuity. I haven't written continuity here. Actually, this is a much better way to see it. This is continuity. Mass in equals mass out. So for us, this would be sum of masses equals 0. And these expressions, actually you can see it much better here. These expressions up here would be sum of velocity times mass flow rates equals sum of forces plus head loss, and which is the same as Bernoulli. So you can see it much better here. This is a viscosity times a velocity, so this is the head loss. This is a density times gravity, so this is an elevation head. This is a pressure change, so this is P over gamma. And this whole term here is accelerations, which is v squared over 2g, which is the same as this inertial force. Well, actually, no. This inertial force here. So, I know you're packing up. And so the only useful thing about this is that we can get a couple of standard solutions. So if we use these 5 equations, we can get 2 standard solutions of use to us. One would be parallel flow between parallel-sided walls of a duct, which actually look a bit like flow within a fracture in the ground. So if you're driving down 322, you'll see lots of cracks in the rocks. And so if you're looking at flow down cracks in a rock, you can characterize it so that you can actually write the permeability of that as being equal to the aperture between that fracture over 12 times the spacing between it, as it turns out. It's kind of a standard result. So if you have a fracture next to another fracture, that they're spaced some distance s apart, and the apertures are b, then you can get the permeability of that very simply as just this expression. So a standard result that says that the fastest velocity is in the middle of the duct, The flow on the edges is 0 because it's attached to the duct itself. And a second standard solution, which is for flow in a pipe, which again has the fluid anchored at the side, maximum velocity in the middle, and so you could convert that to be an average velocity that would look like this. Right? So that the area in this blue area here would be exactly the same as this area here, right? Because velocity times area integrated over this full section, and then divided by the total cross-sectional area. This is just the definition of an average. So in other words, you integrate the velocity over the area, and then you divide by the area. That gives you an average velocity, which would be this length here. And you can use that as a standard result, for instance, to make a magnitude of a pretend porous medium. I know we're going over top. Give me this because we won't meet next week, right? We're online. Imagine taking a porous medium and making it out of a bunch of these tubes where you go from upstream pressure to downstream pressure, like this. And you can write Darcy's law as being equal to K over mu dp dx with a minus sign in it. And you can get an expression for permeability, which by using these little tubes to look at the flow through it, which equals porosity times the diameter of these pipes squared over 32 or 96. And porosity is just equal to the volume of the void space divided by the total porosity volume. So the total volume would be the VT of this cube. The porosity of the void space would be the sum of all these little capillaries. And you can get the permeability out of it by accommodating the fact that this free flow has a shear stress on the side. That's why there's a pressure loss as you go from upstream to downstream. And you can use this open channel flow to do that. That's it. So, not examinable, but we kind of covered it. So pretend energy loss through Darcy's law, even though we're only solving for continuity, mass flow rates in, mass flow rates out, and real losses in the system using what we will call the Navier-Stokes equations, which are these, very complicated, but it's really just the one-dimensional energy equation, which is Bernoulli plus a head loss, and or with a pressure head for the pump head. And if we use those Navier-Stokes equations to solve the free flow problem, we get some complicated solutions which give a maximum velocity in the middle, and some standard results allow us to say something about creeping flows that then we can apply in the subsurface. That's it. So, big picture. Next week we're online. We'll talk about dimensional analysis, which is kind of a strange name because it's actually dimensionless analysis. We work with dimensionless variables. The second time that we met, we talked about Reynolds number, Euler's number, and Froude number, and that we could get those from Bernoulli equation. So we will talk about dimensional analysis, which is just a fancy name for being able to take the variables that control flow in your system, being able to group them in combination so you get non-dimensional combinations of those variables, which has 0 dimensions in mass, length, and time, kilograms, meters, and seconds. And if you provide those groupings, you can figure out a minimum number of experiments to do, so you don't have to do every experiment in the world to be able to characterize behavior of a system. You don't know what need to know what the continuity or energy equations are and solve them. You can just use experiments, some clever experiments, to apply. And you can apply it in fluid mechanics, or you can apply it in any branch of engineering. It's a very common method. Yeah.
When we were doing the string tubes and the equipotential lines, what determines how many string tubes and equipotential lines you draw?
It's defined because Yeah, it's defined by the fact that they have to be perpendicular to each other. So that's a good question. Of course, you could fill this in if I use another color like gray. You could fill every second one in, but then you'd have to add another one of these. So if, yeah, so this would double and this would double. So. And of course, this really isn't a no-flow boundary here, which is what we're assuming, but it would go to some distance, but you'd have less and less influence. So yeah, good question. Go away. So yeah, we're done. So yeah, sorry, I didn't read. So online next week. I was going to be out of town. I think I'll be around, but since we agreed to do it online, then let's do it online. Extra credit kicks in, and it's dimensional analysis.